Excellent. Welcome, lesson 6 on our heat and reactions topic in physical behavior of matter. Okay, we're going to talk about reference table I today, okay, about how much heat is absorbed or released during a chemical reaction, okay. Most of the reactions you need to know are on table I. There's only a few others that you can infer the answers from when it all comes down to at the end. So heat flow in chemical reactions. So heat either comes into, absorbs into a chemical reaction, or is released, exits a chemical reaction. And that's based upon breaking and forming chemical bonds. Okay, so remember, whenever you break a chemical bond, it absorbs heat. Whenever you form a chemical bond, it releases heat. Well, in a chemical reaction, the overall net absorbing or releasing of energy is referenced to as the heat of the reaction. Okay, so overall, after the reaction completes, did more energy get absorbed, endothermic reaction, or did more energy get released, exothermic reaction? Meaning, did it form more stable compounds and become exothermic, or did it form less stable compounds and become endothermic? Anyways, that's a rundown. Endothermic, heat enters the system. It absorbs it up, soaks up the heat. Delta H values from table I would be positive. So the change in heat, delta H, remember, delta means change. H in this case means heat. Change in heat would be increasing. If it's absorbing heat from the surrounding areas, its overall heat would go up. So delta H would be positive. Exothermic reactions, well, that is heat leaving the system. Okay, and therefore the delta H value would be a negative value. If I have less heat now than I did a little while ago, my heat has left me. My delta H value would be a negative value, and the same is true for chemical reactions. If they release heat, produce heat, their delta H is negative. If they absorb heat, consume heat as a reactant, their delta H is positive. So in exothermic chemical reactions, the way we figure out delta H is we always subtract the heat of the products from the heat of the reactants. Delta H means more heat in the reactants, and the heat exits in the system. So if you look at the amount of heat the reactants have versus the heat the products have, if the products have less heat than the reactants did, some heat must have left. That's what makes it exothermic. Opposite's true as well. We still figure out heat of products minus heat of reactants to figure out the overall heat of the reaction. But if our delta H is positive, it means that our products have more energy heat-wise than the reactants did. So they absorbed that energy from somewhere, and heat has entered the system as a result. So when a chemical reaction overall is flipped back and forth, right? So if we write it in one direction, but we reverse it, the heat will be reversed as well. So example, carbon dioxide gas can be decomposed into carbon solid and oxygen gas. Okay, this is on table I. There it is. It says that that reaction is a negative value for delta H, which means it releases heat. But if you were to flip it, it would be a positive system. Okay, so this reaction on the table, carbon solid becoming oxygen gas, makes CO2 gas. Pardon me, I misspoke there. The example I gave you has been flipped. So the delta H sign needs to be flipped too. Remember that. If your reaction is reversed, the sign on your delta H is reversed as well. If you double or triple or half a reaction, the amount of heat has to be doubled, tripled, or halved as well. And you can tell a reaction has been doubled by looking at the coefficients in front of our compounds. On table I, you see carbon solid plus oxygen gas makes carbon dioxide gas, negative 393.5. That's the amount of heat it releases. But the reaction I drew here is 2 carbons plus 2 oxygens makes 2 CO2s. I've doubled the amount of molecules or elements that are involved. So I must double the amount of heat that is involved too. Now I didn't flip this reaction, so the sign stays the same, but the magnitude, the size of it, got doubled because I doubled the size of the reaction. Okay, should make sense. If you double the amount of stuff you're reacting, you would double the amount of heat that is required or is produced. Okay, little logic. Table I, some tours of heats reactions. Okay, so this reaction here, CO, carbon monoxide gas, plus oxygen gas, makes CO2 gas. Delta H was negative, so we know that's exothermic. The reaction didn't have anything to do. It was the same as before, remained the same. The N2 plus the O2 right here in the middle of the chart, making 2NO2 gas. It's positive 66.4, so that absorbs heat, that particular reaction. That means it's endothermic. And again, I didn't change the reaction here. This next one, 2 hydrogen gases. Let's see. Plus oxygen gas makes 2 H2O gas. Yep, it's right there. Negative 483.6 exothermic. Again, I left this reaction the same. Now the last one I flipped, okay? So you won't find this reaction on table I because you'll find its reverse on table I. 2H2O, okay? Liquid, okay? Becoming 2H2, got it, and 1O2, got it. It says it's negative 571 on the chart, but remember, I flipped the reaction, so we're gonna flip the sign, positive 571. That means that this is endothermic now. So the reaction was flipped. It wasn't doubled, it wasn't halved, it wasn't remaining the same, it was literally flipped. That's what you would write there. So the main points of this lesson. Heat is a product or a reactant. Table I tells you that. If the value for the heat is negative, heat was produced. If the value for the heat was positive, heat was consumed, okay? Is a reactant in the ingredients. You can double these reactions, triple these reactions, or flip these reactions. When you double or triple the reaction, you double or triple or halve the amount of heat. When you flip the reaction, you flip the sign for the heat, okay? And that is what I want you to take away from this lesson. Thanks for watching. See you next time. Clicky, clicky button, turn it off.